Okay, so hopefully you took me up on my suggestion to answer this problem conceptually. Now let's do the numerical answer. So let's start out with the constant volume reactor. So we're going to solve both of these. So case one, we'll say constant volume. So by constant volume, I mean that the volume at time t is equal to the volume initially. So first thing I want to do, I'm going to write down my reactor mole balance. The question asks about a conversion. This is a scenario where I can use conversion. So I'm going to write down the mole balance in terms of conversion. So that's going to be dxa dt is equal to minus RAV divided by NA. Okay, so now what I need to do is start filling in these terms. So first I'm going to fill in my rate law. So when I do these solutions, basically this is the way I'm always going to start my solutions, by writing down the correct balance and then starting filling in terms. So we'll say negative RA. Then this was an elementary reaction. So this is going to be equals to K times CA times CB. And we're making the assumption here that it's irreversible. This is A is a reactant. We're writing a rate of consumption, and we would expect a rate of consumption to be positive. So making sure our accounting is proper. Now it's the next step. I have my rate law. Now what should I do? So the next step is to take these concentration terms, and I need to convert them into functions of conversion. So I have multiple variables going on here. I have an x variable and I have a c variable. And right now, if I were to write this all out, I will have a convolution of x and c variables. I need to get my variables to be consistent. So I've decided I'm going to solve my balance in terms of x. Henceforth, I need to rewrite these conversions so that they are in terms of x. So this is a constant volume reaction. Because of that, I know that Ca is equal to Ca naught 1 minus Xa, where I'm treating species A as the limiting reactant. In this case, we know the initial mixture is equimolar in A and B, and the reaction stoichiometry is also equimolar in A and B. Henceforth, I could have picked A or B. I'm just going to pick A because that's what I'm used to. Because of that, though, I also know that Ca and Cb are the concentration of A and the concentration of B. Those are going to be equal over the course of the reaction. So this is a simplification I can make for this special case where A and B are equimolar initially and throughout the reaction. Okay, so this allows me to substitute that in. I can then say Ra is equal to K Ca naught squared 1 minus Xa squared. And now I can substitute this into my equation, dxa dt is equal to K Ca naught squared 1 minus Xa squared times V all over Na naught. There's another simplification I can make here. Do you see it? So I have this moles of A initially on the bottom and the V here. So this is actually, if I take these two terms together, this is 1 divided by the initial concentration. So we can say where Ca naught equals Na naught over V naught, which we've said is equal to Na naught over V. So in that case, I have dxa dt is equal to K Ca naught 1 minus Xa squared. And the next step now is to separate the variables and solve this thing. So to do that, I would say dxa divided by 1 minus Xa squared is equal to K Ca naught times dt. So I'm going to integrate this. So here I would go from 0 to 0.6. And here I am going to go from 0 until time t. And if I perform that integration, I'm going to get t is equal to 1.5 divided by k times Ca naught. So that is how long it would take to get to 60% conversion with my constant volume batch reactor. Okay, so now let's go back and look at the constant pressure case. So we'll say constant pressure. So in the constant pressure case, if we go back and look at the reaction that we're solving, A plus B goes to C. So on the reactant side of the reaction, there are 2 moles, and those react to form 1 mole on the product side. So the number of moles is decreasing over the course of the reaction. So because of that, if we want to maintain constant pressure, that means that the volume is going to change. So we can write this out. So for example, the volume initially at time equals 0 is going to equal to the total number of moles initially times R times the temperature initially divided by the pressure initially. And then at time t, the volume is going to be equal to the number of moles, or the total number of moles at time t, times R times the temperature at time t, and then the pressure at time t. But we know that this is an isothermal reaction, so T equals T naught, and this is a constant pressure reactor, so we also know that P equals P naught. So basically what's going to happen is the volume is going to change because of this change in the number of moles. And in fact, we could write this out. We could say, if we were to relate these 2 equations, we can say that the volume at time t is equal to the volume initially times the total number of moles at time t divided by the number of total moles initially. And in fact, these equations or equations like this are provided in the book. In the book, what happens is this term nt divided by nt naught, that is given a definition. So that's called 1 plus epsilon times x. So this is a book definition. And you've probably worked. In this equation, epsilon is equal to Ya naught times delta, where Ya naught is the mole fraction of the limiting reactant at time equals 0. And delta is the change in the number of moles per mole of limiting reactant that reacts. So delta is the change and that's per mole of limiting reactant. So in this case, we have A plus B goes to C. We have 2 moles over here. We have 1 mole over here. So that means delta is equal to -1. So this, if delta is equal to -1, the mole fraction initially in this case, so initially I have an equal molar mixture of A and B, so that means that Ya naught is what? 1/2. So this means that epsilon is equal to 1/2 times -1. And so that also means then that nt over nt naught is equal to 1 minus x over 2. So our volume is going to change over the course of the reaction, and that's going to influence our concentration. So this doesn't influence our rate law. So the rate law stays the same. So my rate law is still minus RA is equal to KCA times CB, but it is going to influence the concentration of A and B. And it's influencing the concentration of A and B through this volume term. So the volume is getting smaller, and hence those concentrations are getting higher. Okay, so my rate law doesn't change. Now, though, I need to account for the fact that my volume does change, so these formulas for concentration are going to be different than in the constant volume case. So in this case, I'll have Ca is equal to Ca naught 1 minus Xa. But now I need to take account for this volume change also. So that plays into the denominator. So I've said that my volume change is going to be represented by this fraction, or my volume change is going to be represented by this function. So I'm going to put that in the denominator of my equation. And this takes into account that as the reaction progresses, the system volume is decreasing because the number of moles is decreasing. So that's my expression for the concentration of A. Just like in the last case, this is going to be equal to the concentration of B. So the number of moles of A and the number of moles of B initially are the same, and they're going to change identically over the course of the reaction. So they're always going to be equal. So now I have my concentration terms, and I can substitute these into my mole balance. So recalling, my mole balance looks like this. dxa dt is going to be equal to minus RA V divided by NA naught, which is going to be equal to K times CA naught squared times 1 minus XA squared times B divided by 1 minus XA divided by 2 squared times NA naught. And I also know this, so this, my volume, V is going to be equal to V naught times 1 minus XA divided by 2. What this does is now I have 2 of these in the denominator, this term, and I have 1 now in the numerator, so I'm going to cancel out the 1 in the numerator and leave only 1 in the denominator as I do my next simplification. So dxa dt is equal to k ca naught squared 1 minus xa squared v naught divided by 1 minus xa over 2 times NA naught. Just like in the last case, this term is going to be equal to 1 divided by Ca naught. So I'm going to say K times Ca naught, getting rid of the square there, 1 minus Xa squared divided by 1 minus Xa over 2. And that should be my formula. So then I'm going to put all of my x terms over here. I'm going to get 1 minus Xa divided by 2 divided by 1 minus Xa squared. dxa is equal to K Ca naught dt. And I can integrate these. And like in the last case, I'm going to integrate these 0 to 0.6. And here I'll integrate 0 to t. And if I do that, I get that t is equal to 1.208 divided by K Ca naught. So this is for my constant pressure case. So if you recall, so this is T equals 1.208 divided by K times Ca naught. If we go back to the constant volume case, I have 1.5 divided by K times Ca naught. The constant volume reactor hence takes longer to get to 60% conversion than the constant pressure reactor. So why is that? So constant volume reactor takes longer. So, and the reason for that, in the constant volume reactor, so the volume is always constant. We'll say in the constant pressure reactor, as the reaction goes on, the number of moles decreases. This decreases the volume. This increases the concentration, and that increases the rate. So the constant pressure reactor gets to some conversion more quickly than the constant volume reactor. How would this change if this were a liquid phase reaction? So a liquid phase reaction, we always assume constant volume. We'll say we assume. So both cases would be the same. So there really is no constant volume versus constant pressure reactor to think about when the system is in liquid phase.